Okay, welcome to this lecture on polymer chemistry. We'll start by just recognizing that most polymers are hydrocarbon based in nature, meaning that they're made up mostly of hydrogen and carbon, typically. We have some options where many can involve saturated hydrocarbons in their structures. That would mean consisting only of carbons that are singly bonded to four other atoms. And all other intramolecular bonds would also be covalent, therefore. So an example of a saturated hydrocarbon is this ethane molecule, formula C2H6, where we see four single bonded carbons at each, four single bonds at each carbon, and of course that's mirrored to the other half of the molecule. Okay, what is a polymer? A polymer is known as a structure that has many repeating units, thus the term poly and mer. So mer and repeating units will be used interchangeably in today's lecture. And we see here in polyethylene, polyvinyl chloride, and polypropylene that there is a repeat unit highlighted in the blue shaded structure, and that the neighboring units to either side of that are the exact same in their chemical definition and in their bonding. We also show in the case of polyvinyl chloride that we have chlorides at the side chain positions, whereas in polypropylene we have methyl groups at those side chain positions. So this is a methyl group, and those would be side chain positions. And so in polyethylene, all side chains are occupied with hydrogen in that case. And we'll define here that the main chain, which you can see here is intended to repeat over and over and over again down the length of the chain, is the same. So here this main chain is highlighted, and that is another term that you should be ready to witness a lot today. Okay, so polyethylene, polyvinyl chloride, and polypropylene have analogous main chains, but only differ in the side chain composition. Polyvinyl chloride and polypropylene are perhaps closer to one another in that regard. They both have non-hydrogen side chain options, with the former having chloride as the side chain and the latter, polypropylene, having the methyl side chain. Okay, so perhaps you've seen or already are aware that there are natural polymers as well as many synthetic ones, and some of the natural polymers that we won't be discussing today are wood, cotton, leather, wool, and silk. And it's a topic that's very old. In fact, even the Incas were known to extract natural rubber from the bark of trees and form rubber balls for likely entertaining themselves or their children. Okay, so building up towards understanding how we make polymers, we'll show here now the monomer, the single mer, notice the prefix mono, of polyvinyl chloride, and notice that there are four single monomers here, four isolated molecules of vinyl chloride from one another. And clearly, through some polymerization reaction, these are going to connect to one another. So notice the reactivity that we've now got by way of installing a carbon-carbon double bond, and that is a vital feature needed for the polymerization of vinyl chloride. Okay, so polymerization is the chemical process in which individual molecules, or monomers, are converted to large molecular polymers, as our definition. Okay. And so through some detailed polymerization that we'll touch on here today, we'll see that vinyl chloride monomer can become polyvinyl chloride. And we now have an indication for how the polymer name typically indicates the source molecule that was used to make it. So in our parentheses here, vinyl chloride is the monomer used to make polyvinyl chloride. Good. We'll also note at this point that the repeat unit, or the MER, has a well-defined chemical composition. Its formula would be C2H3Cl. This is the same chemical composition as the monomer vinyl chloride, and we will use that information to help us with calculations in our next topic, our next lecture. Okay, so here's another example of polyethylene. So here the repeating unit is shown again in the shaded. So polyethylene, therefore, would come from the molecule monomer that is ethylene. And so in this case, we would install that carbon-carbon double bond for reactivity, and then supply the necessary hydrogens for the repeat unit. Okay, so that's shown here in our chemical structure. You can also show it in a ball and stick model down below, which touches on some other ideas that because of the sp3 hybridization at every carbon site, that we know there must be 109.5 degrees at every bond angle here. And so that is a geometry that's going to be installed at every site down the main chain of polyethylene. Okay, polyethylene is of course related to many other molecules in that sort of structure that we touch on there, and waxes and even other alkane kind of fuels that you might be familiar with are also kind of cousin molecules, if you want, that are just shorter in their chain length or low in molecular weight. Okay, so we've seen here, just to formalize it, that an unsaturated hydrocarbon, things where we have carbon-carbon double bonds or carbon-carbon triple bonds, are useful for making polymers. So these are somewhat unstable, and we can use that reactivity to allow for polymerization. So here, the ethylene allowed for polyethylene, and so to show that, we might show N of those units coming together to make polyethylene, which we have drawn a few times now. So I'm going to show that in a different way, the simplest way we can. Draw my repeat unit or my MER, put a parentheses to show that many of them will be connected down the length of the chain. And if N of them on average have come together, I'm going to indicate that many of them are there with a subscript next to the parentheses to indicate how many of those MERs are down the length of the chain on average. Okay. Acetylene can also polymerize to make polyacetylene, and so typically one of the three bonds in the triple bond is reacted away to provide links to the neighboring MERs. And so in this case, we would do something like this. And again, if N of these units came together on average, we would show an N subscript to indicate how many units there have existed. Some of you might be wondering what happens at the end of the chain. It depends on what termination mode has dominated. And so if the length of the chain is very, very long, it suffices to not necessarily put detail to that chain end, and that can demand rigorous instrumentation to actually identify what the composition of that chain end is. Okay. So in general, what programs for the properties of polymers? Well, it has a lot to do with the chemistry, what units are within the monomer unit, both in the main chain and side chain, how long the chain is, what's the overall molecular weight of the molecule, how big it is, what is the shape, are there stiff bonds or flexible bonds, are there, given the hybridization at some carbons, for example, and what's the molecular structure? This last one's quite complex as well, so that can be further elaborated in talking about linear polymer chains like we've described thus far, where we just imagine these molecules linking up in a linear fashion, but branching is possible, as well as cross-linking, and even network polymers are known as well. If there are isomers, we can have stereoisomers where the side chains could be positioned in some regular fashion, all on one side, alternating or randomly. Or we can have cis-trans options, like in the case of polyethylene. So the cis polyethylene would be reflected with a carbon-carbon double bond that shows its side chain, its pattern having the extension of the main chain down the length, down the same side of the carbon-carbon double bond. So if you recall, there's a 120 degree angle at each hybridized sp2 hybridized carbon, and so this would be a polycis acetylene, and a polytrans acetylene. We would put the polymer pattern across from one another. Okay, so this would be a trans. And so this is also going to program for slightly different properties, as an example. Okay, so just to touch on some of the properties that can be tuned by molecular weight, here's an example of extending a carbon molecule by a CH2 to create a series of molecules. So here we go from methane to ethane to propane. Methane is, of course, natural gas with a very, very low boil point. And as we start building up the chain to be a little longer, we can get the boil point of the gas to approach temperatures that we're used to. Extending the chain even further, we can get that boil point to now be above room temperature. So in the case of pentane, this is now a liquid carbon chain of 5 carbons long in length. And if we keep going, we eventually get to hexane, and can eventually make waxes like you would find in your candles. And eventually, as we keep extending the chain, we eventually get to polyethylene, which is a famous material for its strength, and you recognize it from plastic bags, for example. A thing to put on our radar at this point, and we'll touch on it more in the next lecture, is that the molecular weights that we think of are average. So no polymer material has all chains the exact same length. And so given that, by definition, the molecular weight is the mass of a mole of chains, you see right in here that we're talking about many, many chains. And if the mass is going to vary between units in that mole of chains, we might expect an average molecular weight to be appropriate. So the idea is basically that we still have commonality between the two in that the repeat unit pattern is the same, but the overall length of the chains in a sample can be quite different. And so this average molecular weight will be important. So as a takeaway, not all chains in a polymer are the same length, and we recognize that there's a distribution of molecular weights for every chain, as we reflect above in the cartoon there. So this is important when we consider different polyethylenes, for example, low-density polyethylene, linear low-density polyethylene, all the way up to ultra-high molecular weight polyethylene. All these topics are related to the idea of controlling and specifying the overall molecular weight and the distribution of that molecular weight. Okay, so this helps us now build towards the important thought here of degree of polymerization. So the degree of polymerization is the average number of repeat units per chain. So to drive this home, here's an example molecule where we see that it's related to polyethylene. It's a very short polyethylene in that regard. And hopefully you can recognize the number of ethylene mers in this polyethylene, meaning that there are 1, 2, 3, 4, 5, 6 mers of ethylene with 2 N groups of hydrogen. And so we would term this chain as having a degree of polymerization of 6, given that we have 6 mers in this chain, 6 repeat units in this chain. The degree of polymerization can be calculated by knowing the overall chain's molecular weight. So if we knew the molecular weight of this whole thing, we could then take that and divide it through by the mass of the repeating unit here. Okay, and so for a single molecule that's pure and there is no distribution, it's an easy process. But for an average, for a polymer with a distribution of chain ends, some additional thoughts there are needed. So that's why we put in the detail of number average molecular weight for the polymer and the specific molecular weight of the repeat unit. We can be very precise in that case there. Okay.